problem real quickly. So Jack and Jill ran up a hill. Jack has a weight of 100 newtons and it takes 10 seconds to climb a 5-meter hill. Jill has half the weight, goes to the top of the same hill, but it takes her half the time. So I kind of messed this up a little bit in class, and I just thought it'd be easier if we just kind of went through the numbers of it. So the questions go, how much work does Jack do? So did Jack do? So that work is going to be equal to Jack's change in energy. So if he runs to the top of the hill, he's going to have a change in his potential energy. M times G is his weight, and then I multiply that times his height. So his weight is 100 newtons, and then I'm going to multiply that times the height of the hill. So Jack has done 500 joules of work. That is the change in his potential energy. So now we look at Jill's work. Jill has half the weight. So she's got a weight of 50 newtons, but she's going to go up the same hill, which is 5 meters tall. So she has half the weight, same hill. She's going to do half the amount of work that is done, 250 joules, because she doesn't weigh as much. She doesn't have to put in as much effort to lift herself up the hill. But now we get into this discussion of power. Power is how quickly the work gets done. So if I look at the power formula, and again, that's right up here, it's the rate that work is done. It's how much work is done divided by the time. Jack's work is 500 joules, and it takes him 10 seconds to get there. So divide by 10 seconds, and we get that Jack did 500 divided by 10, 50 watts of power is how much power he expends doing that little task. Now Jill's power, she does half as much work, but guess what? She does it quickly. She's really speedy. So she does it in half the time. So if it took Jack 10 seconds and Jill does half the time, that means Jill does it in 5 seconds. She's speedy. So 250 divided by 5, guess what? That's the same amount of power expended. So they are equally as powerful.